Superconductors are materials that have the capability to conduct electricity with no resistance. This is achieved when the material reaches below its critical temperature, using something such as liquid nitrogen, in order to unlock its superconducting abilities. The cold temperature allows the electrons to pass one another without issue, allowing the electrons to move without resistance. This means they don't make sound or release energy such as heat. This makes them fantastic conductors of electricity more so than regular conductors. Various materials can become superconductors at the right temperature. Materials used for superconducting are organic materials, ceramics, semiconductors that have little resistance when conducting electricity, or metals. Examples of superconductors would be lead and mercury, as they can become superconducting when they reach cold temperatures. One example of a ceramic superconductor is yttrium barium copper oxide. Superconductors were first discovered in 1911 by Heidt Camberlen Oens. Oens was a Dutch physicist who first found superconductivity in mercury. He discovered this when he changed its temperature to that of liquid helium, which was 4 degrees Kelvin, and noticed any resistance had left. He was awarded in 1913 a Nobel Prize for his research. It's safe to say Oens opened the door, allowing more to study and understand superconductors. The next big discovery came in 1933 when Walter Meissner and Robert Oschenfeld found that these superconductors had the capability to repel magnetic fields. The magnetic field couldn't pass through the superconductor, unlike normal conductors. This was known as strong demagnetism, although it's often referred to as the Meissner effect. This results in the levitation of superconductive materials over a magnet. In 1986, Alex Mueller and George Benorves created a ceramic compound capable of superconductivity at 30 degrees Kelvin. This sparked many to find superconductors that could function at higher temperatures. One of the highest temperatures a material can be superconductive is at 138 degrees Kelvin. MRIs use coils of superconducting magnets where the electricity travels through. These magnets create high-quality imaging, although the magnets are quite expensive. Filters and electronics are more efficient than when superconductors are used, as they are fantastic conductors of electricity. While they have amazing properties and can help our world tremendously, they are very expensive to cool down. Liquid helium is often used to cool the material, making it superconductive, but it's a rather long process and costs a great deal of money. This is the main reason superconductors are not used as frequently. Scientists still search for superconductors that can operate at room temperatures.
We all know electrical current is the flow of electricity, but what exactly is electricity and why is it flowing? Let's take a look at copper, one of our favorite electrical conductors. Copper has just one valence electron, making it very easy to push around. Doesn't take very much energy to get those lonely electrons to jump over to another atom. Now, say we took some of these copper atoms and strung them together into a wire. We can take an electron and force it onto the first copper atom. This displaces the electron that was already there and pushes it onto the next atom, which pushes its electron onto the next atom. This process works its way right on down the chain. At the end of the wire, the last electron is sent off out of your wall socket into your cell phone battery or light bulb or whatever device you may be using. It's not unlike those office toys many of us have played with at some point. However, in this case, it's electrons, not metal balls. Unfortunately, electrical current isn't nearly as perfect as our beautifully handcrafted diagrams. Every once in a while, thanks to some wiggling atoms, an electron will go rogue, smash into something and transfer its energy into heat instead of electricity. This loss of electrons is referred to as resistance. Resistance is measured in ohms, which is the symbol shown here. A high resistance can result in the loss of quite a bit of electricity, making some things fairly inefficient. In some high-energy scenarios, it can also result in heat production that can damage the machine that's using the electricity, making high resistance not work for everything. This is where superconductors come into play. They have the ability to achieve zero resistance, not close to zero, exactly zero. No electrons are lost, no heat is produced. This phenomenon takes place when a superconducting material is brought down to its critical temperature, typically around 1 to 20 degrees Kelvin. That's the equivalent of around negative 440 degrees Fahrenheit. These temperatures are often achieved using liquid helium or nitrogen. At these extreme temperatures, things get a bit strange thanks to some quantum mechanical wizardry. The way the particles vibrate in a superconductor ends up in a pattern known as quantum coherence, which quite frankly is a topic a bit better suited for advanced physics or chemistry, but you can think of it as atoms moving in sync. It is this coherence that allows electrons to flow freely without ever losing their energy to heat. In addition to just not having any resistance, superconductors have some very interesting effects when it comes to magnetism. Take it away, Madison.
There are two types of superconductors, type 1 and type 2. Type 1 are typically metals and metalloids. Type 1 is a nearly instant transition to its superconductive state and uses the Meissner effect. The Meissner effect is what gives the superconductors its levitating ability when placed over a magnet. It does this by expelling the magnetic field rather than allowing it to pass through the material, which would result in it getting stuck to the magnet. Conductors let out magnetic fields, meaning the magnetic field doesn't pass through, allowing it to levitate. Normal state conductors' magnetic field can penetrate, leaving them attached directly onto the magnet. Type 2 superconductors are able to reach its superconductive state at higher temperatures. Metal alloys are good examples of type 2s. They use quantum locking, which also makes them levitate. Placing two superconductors above a magnet is where they differ from the Meissner effect. Instead of expelling its magnetic field, type 2 have small defects where the magnetic strands go in between. When placed above the magnet, type 2 superconductors will stay in the same position due to the magnetic strands moving through the material. This is known as flux pinning. Magnetic strands go through these small defects and can move within the superconductor if they aren't accurately locked into place. This can result in superconductors losing energy, and to avoid this, the superconductor will then lock the strands into place, which is known as quantum locking.
In this example, a superconductor is quantumly locked to the magnets below it. Thank you for watching. I hope you learned something new.